Part 5 and the final part today. Analog to digital conversion. Many sensor types, such as LVDT, potentiometer, produce an infinitely variable signal between two limits. For example, 0 to 10 volts, 4 to 20 milliamps, and then 1 to 5 volts, 0 to 5 volts. For these signals to be used in computerized control systems, they invariably need to be digitized. Note that the digitization of analog signals also reduces the effect of external noise on that signal. So once you've taken an analog signal and digitized it, you've made it extremely more immune to interference when you want to transport it over distance. The process of converting analog signals to digital is called A to D, ADC, analog to digital conversion. It's a two-step process, analog to digital conversion. First of all, something called quantizing, breaking down the analog value into a set of finite states. Secondly, encoding, assigning a digital word or a number to each state and matching it to the input signal. Step 1, quantizing. So if we have a 0 to 10 volt signal, separate them into a set of discrete states with 1.25 volt increments. How did we get 1.25 volts? See the next state. So what we've done is said output state 0 will be any discrete voltage between 0 and 1.25 volts. State 1, 1.25 to 2.5. State 3, 2.5 to 3.75, and so on. So let's have a look at this next slide and see where the 1.25 volts come. The number of possible states that you can get out of a particular converter, n, is equal to 2 to the power of n, where n is the number of bits, little n is the number of bits in the A to D converter. So for a 3-bit analog to the digital converter, n is 2 to the 3 or 8. So if we've got a 10 volt signal and we've got 8 steps, we do 10 over 8, we get 1.25 volts. So each step in that digital 3-bit digital converter can resolve 1.25 volts of our analog signal. So we then assign a digital value. We got 3-bit digital value to each of our output states. So state 0, we give binary 0, state 1 binary 1, binary 2 to state 2, and so on, so the computer can understand each of those states. Now, accuracy of A to D conversion. 2 ways to best improve the accuracy of A to D conversion. Increase the resolution, which improves the accuracy in measuring the amplitude of the analog signal. So if we increase the number of bits in the A to D converter, so we went up from 3-bit to 5-bit or higher still, we got more states to be able to represent that 10 volts in, so the steps are going to be smaller. If we increase the sampling rate, which increases the maximum frequency that can be measured. So this analog signal, the A to D converter is sampling that every so often. If we sample it more regularly, we're going to get less error, because we're going to recognise that that's changed quicker. That signal has changed at all. got a diagram. Resolution. Number of discrete values that the converter can produce equals analog quantization size. Q is the voltage range over 2 at the end. V range is the range of the analog voltage that can be represented, and N is the number of bits used in the converter. So in our previous example, Q was 1.25 volts. This is a high resolution. A lower resolution would be if we used a 2-bit converter, then the resolution would be 2.5 volts. A higher still resolution, if we used a 4-bit converter, we'd get a resolution of 0.625 volts. And the Mitsubishi A to D converters on the PLCs that we use here is a 12-bit A to D converter. I don't know if I got the calculations on here for 12-bit, but the resolution will be quite small. So, what we're looking at here is that we get a quantization error. So when you've got a continuous time signal being digitised, there isn't an infinite. We're already showing we're not got an infinite number of discrete values. So the difference between the actual analog value and the digital representation of that value is defined as the quantization error. When we had 3-bit, the black line on these diagrams is the ideal analog signal that we're trying to represent, and step 1 is the digitised value. So we remember it went in steps, and therefore any point on there we could have a small quantization error. If we increase it to 5 bits, so that we have 32 steps, any quantized error is going to be that much smaller. So we are closer to the actual ideal straight line of the analog signal. Sampling rate. Sampling rate is the frequency at which the analog to digital converter evaluates the analog signal. If you look at the second picture, evaluating the signal more often, more accurately depicts the ADC signal. So the blue line is the signal we're trying to depict here. Okay, the left-hand one is sampling at 1 kilohertz. Sorry, 1 hertz. The right-hand one is sampling at 2 hertz, double the speed. So the red indication of the digitisation is closer to the original signal on the right than it is on the left, because it's sampling. Aliasing occurs when the input signal is changing much faster than the sample rate. For example, a 2 kilohertz sine wave being sampled at 1.5 kilohertz would be reconstructed as a 500 hertz in brackets the alias signal sine wave. Nyquist rule. Using a sampling frequency at least twice as high as the maximum frequency in the signal to avoid aliasing. So we ideally sample at twice the maximum frequency we want to measure. Therefore, we'd be avoiding this type of thing. We're not sampling often enough here, so it's making this signal here, the one we're trying to represent, that one, look like this, because we're not sampling it, we're only sampling it there, 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 I think there was a dot, not sampling it often enough to be able to represent it well enough. Okay. Increasing the sampling rate and the resolution, you can obtain better accuracy in your A to D signals. So on the left, resolution 2.5 volts, sampling rate 1 Hertz. On the right, resolution 1.25 volts, sampling rate 2 Hertz. Much better representation. If we increase them further still, which we do, I don't know what the sampling rate is on the Mitsubishi, but I know that they're usually 12-bit. Just do 2 to the power 12 on your calculator. So if that was 10 volts, well, 4096 step size would be 2.4 millivolts per step. Yep. Okay. That concludes my little going over of sensors, coders, position devices.